There's a powerful, invisible, and honestly, a pretty destructive force lurking in our electrical systems. It happens in the blink of an eye, but its effects, they can shut down entire factories and even critical equipment in hospitals. So today, let's dive into this hidden danger.
Here's our game plan. We'll start with the grid's unsung hero. Then we'll uncover the dangerous side effect it can create. After that, we'll look at the real-world consequences, the clever solutions engineers have come up with, and finally, why this all leads to smarter, safer power for every single one of us.
All right, first up, let's meet the component that works tirelessly behind the scenes to keep our power grid stable and remarkably efficient.
So here's a big question for you. How do we stop all those massive industrial motors and transformers from wasting a tremendous amount of energy every single day? The answer is surprisingly simple, but also pretty ingenious.
It's these things, capacitor banks. Now, think of it like the foam on a beer. That foam is what we call reactive power. It takes up space in the glass, but it's not the part you actually want, right? Well, capacitor banks basically get rid of that foam, so the grid only has to move the useful power around. It makes the whole system run so much more efficiently. And the impact here is huge. For a large factory, installing a capacitor bank can slash its power demand by over 20%. I mean, that not only saves a ton of energy, but it also helps companies avoid these really hefty financial penalties from utility providers for being inefficient. But, and there's always a but, right? This efficiency comes with a hidden cost. Let's move on and look at the dangerous side effect that happens every time one of these powerful devices gets switched on.
So under normal operation, the current flowing through one of these capacitor banks is steady. It's predictable. But for just a split second when it's first turned on, something completely different happens. You get this sudden, violent surge. And this chart just illustrates the scale of the problem perfectly. I mean, look at this. A capacitor bank that normally draws about 72 amps can, for an instant, demand a staggering 1,440 amps. That's a surge of 20 times the normal operating current. Just incredible!
So what in the world is happening here? Well, for a fraction of a second, that uncharged capacitor acts like a complete short circuit. It tries to pull in all the energy it needs to charge itself up, like right now, creating this massive temporary spike in current we call inrush. And when I say it's instantaneous, I really mean it. The entire event is over in just 1 to 5 milliseconds. That is an incredibly powerful electrical event that happens literally faster than you can blink. Now, this isn't just some number on a chart. This brief, violent surge causes some very real and very expensive damage in the real world. Let's take a look at the consequences.
This surge is so powerful, it can physically melt and weld switch contacts together, causing them to get stuck in the on position. It can also cause fuses to blow for no good reason, create voltage spikes that wreak havoc on other sensitive equipment, and it slowly eats away at the capacitor itself over time.
And what's really interesting is this quote from a real-world case study. An automotive plant was having to replace these expensive switches every 6 to 9 months because of this exact problem. Think about the cost of the parts, the repairs, and the production downtime. It all adds up.
And the stakes can get so much higher. In one hospital, these same electrical surges were causing voltage dips that made critical equipment, we're talking CT scanners and MRIs, shut down unexpectedly. Sometimes even during patient procedures. That's a whole different level of serious.
So how do you control such a powerful and instantaneous force? Okay, let's move on and see how engineers have developed some brilliant solutions to tame this electrical beast. There are basically two main strategies. The first is to install something called a current-limiting reactor. It acts like a buffer or a speed bump to kind of soften that initial surge. The second, more precise method is called synchronous switching, which is like timing a traffic light absolutely perfectly. And this table here really lays out the trade-offs. The reactors? They're simpler and cheaper, but they do introduce a tiny bit of energy loss. Synchronous switching, on the other hand, is more complex and costs more upfront, but it's incredibly effective and has basically no energy loss because it cleverly switches the capacitor on at the exact millisecond the voltage is at zero. Okay, let's bring this all home in our final section and see how this all comes together to create a more reliable and a much safer power grid for all of us. So what this all really comes down to is reliability. By managing this invisible force, we make sure expensive equipment lasts longer, we prevent factories from shutting down unexpectedly, and we protect life-saving electronics in our hospitals from being disrupted.
And that really leaves us with a final thought. Our civilization is more dependent on stable electricity than ever before. As that demand continues to grow and grow, the challenge of managing these powerful, invisible forces is only going to become more critical to, well, keeping the lights on for everyone.